Hello dear students. In this lecture we are going to discuss about a paradigm of problem solving, that is greedy algorithms. So what are greedy algorithms? A greedy algorithm is an algorithmic paradigm. It means it is a way of solving the problems that follows the problem solving heuristic of making a locally optimal choice at each stage. So at each step, suppose we are here, so we have a number of choices, choice 1, choice 2, choice 3. Suppose this choice is based on the distance. Suppose this is 3, this is 4 and this is 5. So it will take a decision based on locally optimal choice. That is the choice which is best locally. It will not look beyond these three options. It will not look, suppose this is our source and this is our destination. Okay, so it will not look at what these choices lead to. It will just look at the current choices. So it will not look at these next steps. It will only look at the locally optimal choice. Locally it has three choices, and out of these three choices this is the best choice. So it makes this best choice at each step, at each stage, with the intent of finding a global optimum. The overall goal is to find a global optimum, right? So at each choice, at each stage, a choice is made based on local criterion, and it drastically reduces the search space. How it reduces the search space? For example, if we chose this path, so all these paths and the further paths which are emerging out of these, they will be ignored. Okay, so it drastically reduces the search space in this manner. And another thing to note in greedy algorithms is that never go back and revise a choice which has been made earlier. Okay, so if we made a choice 1 here and we reached at some other point number 2, so we will not come back to 1 again and revise its choice. Instead of 1, we now cannot make it 3. Okay, so we have to go with this. So this is an introduction to greedy algorithms. So now we are going to discuss the first problem which can be solved using the greedy algorithms, which is finding the minimum number of coins. Okay, so what is the problem statement? Problem statement is that we have been given a value v. Suppose v is equal to 70. Okay, and we want to make change for rupees v. So we want to make a change for 70 rupees, and we assume that we have infinite supply of 1, 2, 5, 10 and 20 valued coins. So we have a supply of a number of denominations. Okay, so here we have this list of the denominations which we have. So this list can be changed. Okay, so in this particular example it is this list, but your list can contain only these values. Okay, your list can contain all ones also, but we have infinite supply of these denominations. Okay, so we can use as many as we want. Then the question is, what is the minimum number of coins or notes which are needed to make the change? So we want to make a change for 70. What will be the minimum number of coins through which we can make a value 70? This is the problem statement, and the solution to this is greedy approach. And the idea is, start from the largest possible denomination and keep adding denominations while the remaining value is greater than 0. Okay, so we pick the largest coin or note which is available to us, right? So for example, let us consider the previous example: 1, 2, 5, 70 and 20. So here let us start with 20. Okay, so we picked up 20. This is, you can note that this is already sorted. Okay, so we will start at the end. We will pick 20, and after picking 20, the value which is left is 50. Okay, so again we will pick 20, another 20, and now we are left with 30. Again we will pick 20, now we are left with 10. Now as 10 is greater than smaller than 20, we cannot pick a 20 again. Now we move one step backward in this array of coins and we pick 10. Okay, 10 minus 10 is equal to 0. So now we are left with 0. It means to make a value 70, we needed 4 20s and 1 10s. Okay, so this is how we solve this problem, and you can note the thing that this is a greedy approach. Why is this a greedy approach? We are starting with the largest denomination which is available to us. Okay, so we simply take the largest value. That is our greedy approach. We do not look at any further denominations which are available down the list. Okay, so these are the steps for solving this problem using the greedy approach. So first of all, sort the array of coins in decreasing order. Okay, in the previous example we had the decreasing order. Okay, already the list of denominations was sorted in the decreasing order. It was in the increasing order. If it is in the increasing order, then you can start at the last index. If you are sorting it in the decreasing order, then largest denomination will be at the first place. So you can start picking the denominations at the first index, that is the 0th index in the array. Initialize the result as empty. Okay, result means the set of coins which you are picking. Initially you have not picked any coin, so this set is empty. Then find the largest denomination that is smaller or equal to v. So we have 20, 10, then 5, then suppose 2 and 1, and value v is 70. So the same thing, largest denomination that is smaller than or equal to v is 20. So we pick it and we add the denomination, this denomination 20, to the result. Okay, then we subtract the value found, that is we subtract 20 from the value. Now we are left with 50. Okay, so if v becomes 0, the value becomes 0, then we are finished. We have done the complete procedure. Otherwise, repeat the steps 2 and 3 for new value of v. Actually it should not be 2 and 3. We will repeat the steps 3 and 4. Okay, so again we will find the denomination which is smaller than or equal to v. So this is 20 again, and now we subtract 20 from here. We are left with 30, and again we will repeat 3 and 4. So find the largest denomination. We again found 20, and then we subtract 20 from 30 and we are left with 10. Then again find the largest denomination. Now we move our cursor here and we have found 10, and now we are left with 0. Okay, so this is the set which contains the denominations which we picked for making a value equal to 70. Okay, so this is another example. Here we are showing the number of iterations also. So in the first this you can see these are the denomination. D means denominations which are available to us. 1, 2 and 10, these are the denominations which are available to us. Okay, and n is equal to 15. Here n means the value which we are trying to make. So we are trying to make a value of denominations equal to 15. And I is 2. I is 2 means as this array is sorted in increasing order, as I said earlier, we have to start at the last index. So this is the index in array D. Okay. So what we will do, we are already at the largest denomination. We will pick D2, which is equal to 10. Why? Because 15 is greater than or equal to 10. Okay, so this is step number 3 in the previous procedure. Okay, and then we decrease n by 10. Okay, so now the value which we are left with is 5. Okay, now add 10 to the set S. So our set of denominations now contains a denomination 10. Okay, so now we move to the second iteration, and here in the second iteration I will be equal to 2. So we have moved our cursor to not I equal to 2, I was 2 here, now I is 1 and n is 5. Why we moved our cursor? Because now we are left with value 5 and this denomination was 10. So this will not serve our purpose. We have to step back inside the array. Okay. So now we will pick D1 equal to 2 as 5 is greater than or equal to 2. Okay. Now we will decrement 2 from this value and we are left with 3. Okay. And 2 will be added to our set. Okay. And again we are at the same iteration 2. Why we are at the same iteration? Because we are left with 3 and this iteration 2 means the pointer is at 2 inside array D. Okay, this will serve our purpose. We do not need to move this cursor a step back. Okay, so we can stay here, and now we will pick 2 and decrease this value by 2. So 3 minus 2, we are left with 1. So now the value which we are left with is 1, and this 2, as we have picked it, we will add it to the set. Okay, so now we are left with value 1, and now we have to move to the next iteration, that is iteration 3, because this will not serve our purpose. 2 is greater than the value which is left. Okay, so we have to move a step back, and now we will pick D0 equal to 1 as 1 is equal to 1 is greater than equal to 1. Okay, so we will subtract 1 from the value and now we are left with only 0. Okay, and we also add 1 to this set. Okay, so the coins or the denominations which we needed for making a value n equal to 15 are 10, 2, 2 and 1. Okay, so now we move on to the pseudo code for this, and here D is the array of denominations. As in the previous example, it was 1, 2 and 10 for example, and M is the number of coin denominations. How many denominations you have? Here 1, 2 and 3. There are 3 denominations. And N is the amount of money or the value which you want to make. In the previous example, it was 15. And S is the array which will contain the denominations which will be picked up by this greedy approach. Initially, S is empty. Now, the first step is sort the array D in ascending order of coin denominations. Okay, so it is not necessary that it will be already sorted. You have to sort it. So 1, 2 and 10, now it is sorted, and now we run a loop, and as we saw in the previous example, the loop variable is I, and I is starting at the last index. Size is 3, so I will start at 0, 1 and 2. So initially I is at 2, okay, and I will move till 0, okay. So this is running m times, this for loop. And let me also write the complexity of sorting. So if we use algorithm like quick sort or merge sort, then the complexity will be order of m log m, where m is the number of coin denominations, right? Okay, so this will be the complexity for sorting, and it is running m times, and inside the for loop there is while loop. While loop means whether you stay there, whether the I index will stay at this position or will it move. So while n is greater than equal to di, okay, so while your number which you are picking, for example, initially it was 15 and di is, I is at location 2 and the value at di is 10, okay. So this is true, initially this is true. So what you will do, you will add s is equal to s plus s union, whatever in the s it will stay as it is, but also we add di. So di is 10, so we add 10 here, and n is equal to n minus di. So n is equal to, initial value was 15 minus di, now it is 5, okay. So then we reach the end of this loop, and again when the loop runs, again we check n is greater than equal to di or not, to decide whether we have to stay at the same index I or whether we have to move to the previous index, okay. So now n is 5 and di is 10, so this condition is false. It means we cannot stay at this index anymore, we cannot stay at index 2 anymore, we have to move backwards, okay. So this while loop will not be executed, and so this if condition is also not true, so for loop will be iterated for the second time, okay. So m minus I, initially it was m minus I, so it is m minus I to 0, it means this is a descending loop, okay. So now we will move the loop index I one step backward. So now I is pointing at index 1 inside this array, okay. So now if we check n is greater than di or not, so now n is 5 and di is 2, okay. So this condition is true. So what we will do, s is equal to s union di, so 2 will be added to the set, and then n is equal to n minus di. So n was 5 minus 2, now we are left with 3, okay. So again this while loop will iterate, and now again we check the condition, is n, now n is 3, greater than or equal to di? Yes, again this is true. So again we add 2 to the set, and now we decrement 2 from n, and here we are left with a 1, okay. So again while loop will reiterate, and now n is 1. Is 1 greater than equal to 2? No, this is false. So now this while loop will not run, and if condition is already false, so again this for loop will move to its next iteration. It means it will be decremented, the loop variable I will be decremented again, okay. So now we are at this point. Okay, so di here, I is 0. Okay, now we compare it with d0. So what is d0? D0 is 1. Okay, so this condition is true. So we will add 1 to the set, and n is equal to n minus di, that is 1 minus 1. Now we are left with 0. Okay, so again the while loop iterates, and now n is 0. Okay, and this condition is false. This condition is false. We come out of this while loop, and then we encounter this if condition here. So if condition is now true, so n is 0. Now we have reached n equal to 0. It means break. Okay, so we come out of for loop, and at the end we return s, the set we got. Okay, so these are the coin denominations which we got through this algorithm, right? Now the complexity analysis of this algorithm. First of all, let us talk about the time complexity. So as I already told you, for sorting the array of coin denominations, we need m log m time, and the for loop, it will run order of n time in the worst case. So we are here talking about the worst case. What might be the worst case? Worst case will be when you have, suppose, only one coin denomination, and the value of that denomination is 1, and suppose you want to make 15 now. Okay, so how many ones will we needing? 1 plus 1 plus 1, 15 ones we will need. So this is the worst case. Okay, so in the worst case, we may need n coins to make the change. So here n is 15 and we are needing 15 coins. So this for loop, in the worst case, it will run order of n time. And what will be the overall complexity then? Overall complexity will be the complexity of sorting, that is order of m log m, plus the complexity of the for loop in the worst case. Okay, but this m is much smaller than n. Okay, m means the number of coin denominations which we are having, and n is the value which we are trying to make. So n can be any value, it can be 1000, 10,000 and so on. Okay, so m, the coin denominations are very less as compared to the value which we are trying to make. So overall we will say that we can ignore this, and the time complexity is order of n, right? But there is another algorithm through which we can implement it in much more efficient manner using m log m complexity, and that is using the dynamic programming. Okay, so the complexity of finding the minimum number of coins using greedy approach is order of n, while using the dynamic approach it can be order of m log m. Okay, and the space complexity, we are not using any additional space, we are not using any additional array or any other data structure, so it is constant, right? And now we move on to the limitations of this. The greedy algorithm may not provide an optimal solution for some of the denominations. So for example, here denominations are 1, 6 and 10, and n is 3. The value which we are trying to make is 3. So what will happen? Initially you will point at 10. Okay, so you will see that 10 can be picked, right? According to the algorithm, 10 can be picked. So we pick 10 and we subtract 10 from the value. Now we are left with value 3. Okay, so now we cannot pick 10 because 3 is smaller than 10. So we move backward, we cannot pick 6. We again move backward, we can pick a 1. So we pick a 1 and subtract 1 here. Now we are left with 2. We again pick a 1, we are left with 1. We again pick a 1, we are left with 0. Okay, so the denominations which we picked are 4, 1, 10 and 3 ones. Okay, but can there be a better solution for this? We have to make the value 13. So how can we pick these denominations? There are 4 denominations here, 4 coins. Okay, can we do this in less than 4 number of coins? Is there any solution for that? If we do not pick a 10, instead we pick a 6 and again pick a 6 and pick a 1, then this results in 13, and now we needed only 3 coins. Okay, so this is the limitation of this greedy algorithm approach, and such kind of a solution is possible if you use dynamic programming approach. Okay, so what is the reason for this? The reason is that the greedy algorithm builds a solution step by step by looking at the local choices. So it is very greedy. So it looks at only the local choice. Initially it is at 10. So the local choice to it is pick 10. Okay, 10 can be picked, so it will pick 10. Okay, it will not see in future, it will see at present which is the best possible choice. Okay, so at each step it picks a locally optimal choice in anticipation of finding a globally optimal solution. As a result, greedy algorithms sometimes gets trapped in local optima and is unable to provide a globally optimal solution.